Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So Umar is not new to Microsoft Research. He spent the summer in Mountain View working with Lina Mishra and others on search-related problems. He also spent the summer in AT&T working on voice-activated interactive applications. Right? Mm-hmm. Umar won several prestigious awards, including the Best Student Paper in UAI 2007, the Computer Science Department Award in Princeton in 2004. He also won the Google Student Award in the Machine Learning Symposium twice in 2007 and 2009. Therefore, without further ado, let's hear from Umar Syed about robust semi-supervised learning.
Okay. Thank you, Ronnie, for that very kind introduction. So as Ronnie said, today I'll be talking about robust semi-supervised learning. This is joint work with Ben Taskar at the University of Pennsylvania. So just to set the scene a little bit, let me review supervised learning, which is the oldest, most traditional learning model in machine learning. So in supervised learning, we are given a training set of examples, and a labeler carefully examines this set of examples and reveals all the labels of the examples to a learning algorithm. And the learning algorithm's job is to try to fit a function that predicts the labels of these examples as accurately as possible. But it has been commonly observed that labeling examples is an expensive and time-consuming process, and many alternative approaches to supervised learning have been proposed to deal with this, and one of the most popular is semi-supervised learning. So semi-supervised learning is based on the observation that while labeled data is expensive, unlabeled data is typically quite cheap and easy to obtain. And so our learning algorithm should try to exploit this abundance of unlabeled data. So in semi-supervised learning, we're given a training set of unlabeled examples. A labeler examines the examples and reveals the labels of some of the examples to the learning algorithm. Now, a question that sort of immediately comes to mind is, how are the examples selected to be labeled? And in most analyses of semi-supervised learning, and the way most algorithms are derived, it is assumed that the examples to be labeled are chosen randomly and usually uniformly at random. That is, the unlabeled data and the labeled data are drawn independently from the same distribution. But in most naturally occurring partially labeled data sets, the examples that are labeled are not selected at random. So consider a website like Flickr. Users on Flickr can tag pictures with tags that indicate the content of the picture. Something similar happens on Facebook. You can tag pictures. You can also indicate whether you like the picture or not. And the process by which users are selecting pictures to label is unknown to us, but it's almost certainly not a random process. In fact, most websites on the internet that are soliciting user feedback are generating in one way or another a partially labeled data set, and the examples that are labeled in that data set are selected according to a process that is difficult to model and difficult even to know. And let me just point out that in all these examples that I'm showing you, the user selects an example to label not in a sort of sterile, isolated environment, but rather in the context of a web page, typically in the context of other examples. So this selection bias, the selection bias by which the user chooses examples to label, is highly correlated across examples and seems difficult to model. And so today I'm going to talk about an approach to semi-supervised learning that attempts to totally lift this modeling burden. So we're going to assume that the examples in the training set that have been selected to be labeled are chosen arbitrarily, even adversarially. And so we don't want to make any probabilistic assumptions about which examples are labeled. Within this framework, I'm going to derive some generalization bounds, tight upper and lower generalization bounds on learning in this framework. And using those bounds, I'll derive an efficient and scalable algorithm that can learn a predictor using partially labeled data sets. And then towards the end, I'll describe some experiments that illustrate the benefits of our approach. And these experiments will illustrate that our approach is more robust than traditional semi-supervised learning algorithms when the labels are provided by a particularly unhelpful or confusing labeler. Okay, so here's a roadmap of the talk. After I describe robust semi-supervised learning in detail, at the end I will briefly discuss some other projects I've worked on related to bandit algorithms. I've worked on these projects during both my PhD and my postdoc, and I think some people here might be interested in perhaps talking about these projects later, so I'll just kind of briefly summarize them at the end, and maybe we can discuss them later. Okay, so let's talk about the learning model. So what do we want from this learning model? Remember that we want to lift the burden of having to model how users select examples to label. So we don't want to make any probabilistic assumptions about how those examples are chosen. Additionally, and somewhat orthogonally, we don't just want the labeler to be able to give us discrete label information about each example, but also to be able to tell us some global information about the labeling of the entire data set. And this kind of soft global label information is going to be particularly useful for our experiments. And I'll describe it more in detail a little bit. So here's our framework in some more precise detail. So we're given a training set of examples, x and y. Here, x and y are vectors. So x is a vector of example, and y is a vector of labels corresponding to those examples. The labeler examines the training set, and then he reveals to the algorithm a label regularizer function. Now, this function is chosen arbitrarily, perhaps even adversarially, from some known function class, and the function is going to encode all of the information that the labeler wishes to reveal to the learning algorithm. So the semantics of this, what is this label regularizer? The semantics of this regularizer are that of a asymmetric penalty function on labelings of the training set. So in other words, if R assigns a large value to some full labeling of the training set, this means that that labeling is not likely to be the correct labeling of the data. If R assigns a small value to some complete labeling of the training set, then then that labeling may or may not be the right value, the right labeling of the data set. So in other words, roughly speaking, the minima or near minima of the function R, which is defined on labeling space, are possible labelings of the data set.
This doesn't talk about choice. Maybe you're to get to that in the next slide. This just seems to talk about, here's a function. Okay, so I'll let you go.
Right, so we're just given this function. That's it. So just
one kind of clarifying question. How is the expert supposed to give you this function? This is given to you by something. And so what? Give me a sense of how the expert is going to come up with this function. And
so you're going to need to be able to follow the gradient for this function.
Right. But how are we supposed to expect an expert to give you this function?
I'll give you some examples of specific functions, and maybe that'll clear it up. Yeah. But so that'll be the next slide. But just to recap, this is the learning model. Again, so a training set x and y is drawn independently from some distribution. The labeler looks at that training set, replaces the labels with this regularizer function, and then that is the only information that the learning algorithm sees. Okay, so here are some examples. So suppose this framework is quite general, and it can capture several existing approaches to semi-supervised learning. So here's an example. Suppose that the labeler is going to tell you for each example a set of possible labels that this example could have. So a regularizer function R that would encode that information is a function that assigns 0 to any full labeling of the data set that is consistent with these sets, and infinity otherwise. This should be, it looks like in the transfer some symbols got lost. So this should be infinity and this should be element. Sorry about that. Oh yeah, oh boy, I hope this doesn't happen too much. Okay. So here's another kind of information that, that a regularizer function R could encode. So suppose the labeler wants to tell you that, to give you a similarity measure on examples. And he wants to assert that two examples that have similar, or that are similar have similar labelings. So this is basically what's called Laplacian regularization. And it can be encoded using this form here. And notice here that I've replaced a labeling of the data set Y with Q, which is a distribution on labelings of the data set. This is sort of basically a soft version of a labeling of the data set. And for the rest of the talk, when I mean a labeling, I really mean this softer version of a labeling, distributions on labelings. Another thing the labeler could tell you is he could give you some, he could tell you the expected values of some features under the true posterior distribution. And this kind of information is called posterior regularization. And this is yet another approach to semi-supervised learning. I hope that answers your question. These regularizers can also be combined. For example, if he wants to tell you, if the labeler wants to tell you a set of labels per example and also similarity information, then that can be encoded using this simple sum.
So if I wanted to just, well, not lie, but let's say I wanted to be really adversarial and I wanted to choose the worst possible examples in each class to show you, how would I encode that in an R? I want to just go and I want to mess you up and I want to say, let's say there's two overlapping Gaussians, and I want to take the labels from the wrong.
Right. So I'm gonna do an experiment with exactly that kind of noise
so
later.
Do you express R? How do you express that R? Is it?
So you would say that. So he wants to tell you information, say about two examples. Mm-hmm. So labelings that are consistent. So any labeling, the function will be independent of what labels it assigns to the other examples. Mm-hmm. And for those two examples, it'll have a low value for those labelings that you think that you say are allowed, mm-hmm. the labeler says are allowed, and a high value for those that it says are not.
So how do you? Okay, we'll keep going. Keep going.
Okay. So one question you might want to ask is: so I've just explained how several existing approaches to semi-supervised learning can be put in our framework. So how is this any different from ordinary semi-supervised learning? So all existing, at least the ones that we're familiar with, approaches to semi-supervised learning are optimistic in the sense that they tend to find a predictor that has good performance on the best possible complete labeling of the partially labeled data set. And our algorithm, as I'll demonstrate to you, really finds the best predictor that has the best performance for the worst possible complete labeling of the data set. And so in this sense, existing approaches are optimistic, while our approach is more pessimistic. And this is particularly good for scenarios where the examples that have been revealed are not representative or confusing or misleading in some way. And our experiments will illustrate this. And moreover, as kind of a bonus, this pessimistic versus optimistic approach has the effect of convexifying some existing approaches to semi-supervised learning that are non-convex. For example, posterior regularization, one of the examples I showed you, is a non-convex formulation of the problem, and our pessimistic approach convexifies that approach. Okay, so I hope the learning model is clear. So now let me give you a few bounds about this model. So before I kind of jump into stating what the theorems are, let me step back and ask what is the point of these theorems. So I'm going to give you an upper and lower bound on generalization error in this learning model. And the algorithm I present later in the talk is going to minimize the upper bound. And because this upper and lower bound are going to be almost tight, this will show that our learning algorithm is near optimal. In other words, the right thing to do. Okay. So here's the upper bound. So let's, again, x and y is a training set drawn from some distribution. And L is the loss of the parameter that you're trying to learn. It could be log loss or hinge loss or something like that. And R is that label regularizer function that encodes the information. Then with probability 1 minus delta, we have the following somewhat difficult to parse upper bound. But luckily, the bound on the right-hand side is the sum of 3 terms. And each of these 3 terms, I think, has a nice intuitive interpretation. So let me walk you through it to help you understand what this bound is really saying. So the first term is a maximization. And this maximization is balancing between two objectives. So this first part of the first term, this is the expected loss of the training set under labeling Q. And this is the penalty, essentially, that the regularizer assigns to Q. So this maximization is trying to maximize the empirical loss that we observe subject to this penalty. So when R has, and so this first term, will tend to be large whenever R has a lot of minima, because that gives it, or near minima, because that gives this maximization more opportunities to be large, more places where it can be maximized. So in other words, this term will tend to be large whenever R is ambiguous. Many labelings are possible or allowed. The second term is the penalty that is assigned by the regularizer function to the true labeling of the data set. And so this term will tend to be large when R is misleading, when the labeler is lying to you about what the true labeling is. And the last term is a term that goes to 0 as the number of samples goes to infinity, and this term comes from standard arguments from uniform convergence. And so taken together, what this bound is saying is that as the number of examples goes to infinity, the loss of any parameter is bounded by the ambiguity and misleadingness of the label regularizer function that the labeler gave you, which is a sort of expected kind of result. Okay. So this is the upper bound. Now it turns out that without further assumptions, we're not going to be able to prove a matching lower bound. So what I'm going to describe to you is a set of what I hope you will agree, are natural assumptions about the behavior of a labeler. And under these assumptions, we'll be able to prove a tight lower bound. Okay. So there are basically 3 assumptions. So the first assumption is basically a truth-telling assumption. So here's the function R that the labeler gives you. And let this be the true labeling of the data. And the assumption is that the true labeling is within epsilon of the minimum of the function. In other words, the labeler is not highly misleading about the truth. I should perhaps also point out that this function R typically will have many minima. So it's not enough just to identify the minimum of the function to be able to recover the labeling.
Sorry, I have a question. Maybe I'm just misunderstanding the setup a little bit. Because so the labeler is handing you both the regularizer R and some set of labels.
No, just the R.
Just the R.
The only information you get is the R.
But isn't this? But how does this? Because earlier you said that you're taking a very pessimistic view of what the labeler is doing, and then here it seems, and maybe I'm misunderstanding, but it seems that you're kind of assuming that they're not misleading you by virtue of the R.
Oh, right. So the pessimistic view. So that's a very good question. So I would say that the pessimistic view is not so much a consequence of the model, but rather a consequence of the bounds that I'm describing to you. So this upper bound is pessimistic because we have this max over in essentially all possible labelings that are essentially consistent with what he told you, right? And I'm going to describe to you as a scenario where this bound is tight.
So you're saying worst case in terms of given the setup with that particular circumstance.
That's right. That's right.
But the R itself is not trying to really lead you.
Right. So I should make a distinction between being misleading and being ambiguous, right? So this is saying that the labeler is not misleading, but he can be as ambiguous as he wants.
I had one confusion also on the previous slide. The loss. This is the loss of the model, assuming Q is the correct labeling.
On the right-hand side, that's right. That's right.
On the left, the first term of the right hand.
The first term on the right-hand side.
Okay.
But we're right. Q is a state. Yeah. Okay. It's extrusion over.
That's right. So draw an example from the training set, and then draw its label according to Q. Okay, so again, the first assumption is that the labeler is not too misleading. The second assumption is an assumption about the stability of the labeler. So if I have two training sets and they are very similar to each other, and I'll explain what I mean by similar in a second. If they're very similar, then the labeler will give me the same information for both training sets. And by similar, I mean think of those two training sets as empirical distributions in input space. If those two distributions are close by this amount that we're going to parameterize by lambda, then that's what we mean by close. So that's stability. And the last assumption is kind of an unusual one, but it's necessary, and that is that what we call the no coding assumption. And that is that the labeler can't hide the true labeling in some clever way in the function R. We want to exclude this possibility because if he hides the true labeling in a clever way, then a very clever algorithm might be able to recover it, and we have no hope of showing that our algorithm is optimal. So let me just give you an example of a clever hiding of the information. So consider a data set where the examples have binary labels, and the labeler is going to erase some of the labels and not erase others. So if there are m examples, there are 2 to the m possible labelings, and there's also 2 to the m possible ways to erase labelings. So there could, in fact, be a 1-to-1 mapping between labelings and erasure patterns. And a very clever algorithm could invert that mapping and recover the truth. Now, obviously, this is a highly artificial, unrealistic setting, and this is exactly the kind of artificial thing we want to rule out. Because if we don't rule it out, then I can't show that the algorithm is optimal.
What would be the proper definition of no assumption?
So the proper definition is that R assigns some labelings finite value and other labelings infinite value, right? So let's call things that are finite allowed and things that are infinite not allowed, right? The penalty means it's not allowed. So the assumption is that no algorithm can conclude that a labeling that is allowed is not allowed. It is not possible. So if the regularizer assigns a finite value to a labeling, then it's possible. That's the assumption.
Like in the derivation section, you showed the example of like ratings on Amazon.
Yeah.
So I think there's this effect where people tend to rate things that they either love or hate. Right?
Yeah.
And so that would be kind of a situation that seems to be analogous to a mapping between, not a deterministic mapping, but nonetheless a mapping between labelings and erasure patterns, right? Because what's happening there is essentially people are erasing the 3-star ratings.
That's true.
And leaving the 5 and 1s behind.
Yeah, that's a good point. That's a good point. That's true. That's a good point. I would argue with that.
Your lower bound cannot include that, or can include that?
No, it's fine with that because, so what would the R look like for that setting? So,
I think you could just say that the cases of 3 are ambiguous.
Yes.
This is fine.
Well, no, it's more than that, right? Because you're saying that the cases that are left unlabeled, it's actually telling you something about
The actual label.
the actual label.
but it's right. So if
Clever enough.
no. So if it were the case that anything unlabeled
Yeah.
is definitely not a 1 or definitely not a 5.
Yeah.
Oh, with high probability, right? Yeah.
Well, even no, I think.
With high probability is okay. So as long as it's soft, it's okay.
Yeah, I think so. I mean,
Oh, okay.
so the assumption does not involve probability.
I see.
The no coding assumption.
So there can't be a deterministic way to determine
That's right.
labels. Okay, so
And conversely, a totally fine R is R of truth equals 0. I mean, you can still do full labeling, right?
Absolutely, yes.
So R of truth equals 0, R of everything else equals infinity.
Okay, that's the supervised setting.
Right. And that still works.
And that's true. Okay, so under these 3 assumptions, which I hope I've convinced you are reasonable, we have the following lower bound. So if the number of examples is at least this many, here lambda is from the stability assumption, then with at least constant probability, no algorithm is guaranteed to have generalization error that's more than this much better. Excuse me. So in other words, that's this much better than the upper bound. In other words, there's no algorithm that can guarantee with high probability a generalization error bound that's more than this much better than the upper bound that I showed you. And again, here lambda is from the stability assumption, and epsilon is from the truth-telling assumption.
No, the square root. Is it real square root or is it whole square root? I'm just curious if it actually cancels
it's probably, you're right. It's probably.
But does it actually cancel the term? Does it cancel the term in your upper bound?
It's the same term.
Yes, so this is saying that you can't be more than max over q of L of theta L. Q theta minus epsilon.
No. So the gap will be twice. So, so in other words, the upper bound has a slack of this much,
Yes.
and the lower bound has a sort of complementary slack below it. So the gap is twice this term. Yeah.
But it goes.
Yes, it asymptotically goes to 0. That's right. So asymptotically, the gap is epsilon. Okay, so now that we have our matching upper and lower bounds, we're ready to derive an algorithm. And the algorithm is really simple. Now that we've shown that the upper bound is tight, at least under some reasonable assumptions, the algorithm is just going to be find the theta that minimizes the upper bound. And hopefully we've argued that that's the right thing to do. And we're going to minimize the upper bound while controlling the norm of theta to help with generalization error. And so here I've just plugged in the upper bound from the previous slides, discarding terms that are independent of theta. Oh, so right. So how could I minimize this objective? So one thing I could do that perhaps some of you are familiar with is I could try subgradient descent. I want to minimize this function. This function is not differentiable, but I can find its subgradient at various points, and I can follow the subgradient until I find the minimum. But something that we found seems to work better is the algorithm I'm about to describe, which is essentially we're going to describe a 2-step algorithm for finding theta star, the theta that minimizes this objective. And this algorithm assumes that both the loss function and the regularizer function are convex. And all of the examples of regularizer functions that I've given you so far are in fact convex. And the algorithm is called game because we use a game theoretic theorem in the proof of its convergence. So here's the algorithm. Essentially what we're going to do is, so we have this mini-max objective. So we're basically going to solve the problem inside out. So by solving it inside out, I mean I'm going to swap the min and the max in the objective. Okay? And now I'm going to find not the best theta for the worst possible labeling, but rather the worst labeling for the best theta. In other words, I'm sort of changing roles. I'm no longer the learning algorithm. I'm like nature trying to mess up my learning algorithm. And that worst labeling is called Q star. And then the next step is to find a best response. So assuming that this worst labeling is indeed the true labeling, I just find the best theta for this Q star, this worst labeling. Okay? So I'm kind of solving the problem inside out.
So you do kind of like plug our model when you kind of iterate between the steps?
No, not exactly. I'll describe what I'm going to do, but this is the high-level argument. So there's a couple of questions. First of all, the first question is, is this what is this buying us? Like, why is turning the problem inside out helping in any way? But an even more basic question is that, why does this give us the right answer? In other words, why is the theta star here the same as the theta star for the original objective, right? And so let me address that problem first. So first of all, is it clear what I mean by solving the problem inside out? Okay. And the reason why this works is that Q star, that worst possible labeling of the data, in fact, uniquely determines theta star, the parameter that we're interested in.
As long as Eleanor convex.
Yes, that's right. Well, a bit more than that. Strongly convex is the term. Yeah. So here's exactly what you're talking about. So here's the objective from this second step of the algorithm. So I found my Q star, the worst labeling, and indeed theta star is the unique minimum of this objective. And this function is strongly convex because of the regularizer alpha that I've added to it. If I had not added that, it might be just convex. It could have flat regions. But due to strong convexity, it's the unique minimum. But we have kind of a problem, which is that no algorithm is going to find the exact minimum, but rather only an approximate minimum. And at least in this picture, the true minimum and the approximate minimum are quite far apart, because when the function is just almost flat, you have this problem. So what we do, and this is sort of done in more than one place, is that if you just increase alpha, you make the function more strongly convex, and then you can be sure that any approximate minimum is going to be close to the true minimum. And so this is the effect there. And so this kind of illustration, I hope, explains the convergence guarantee we have for the algorithm, which is that if both steps of the algorithm, this inside-out approach, find epsilon approximate solutions to the problem, then the theta that's output by the algorithm is going to be this close to the parameter that you're after. And the precision of your answer is governed by how approximate the answers were, and also this alpha. So you made that alpha to make the thing more curved so that the approximate answer was close to the true answer. And then you have to make epsilon at least that big to drive everything close. Go ahead.
You said you found this to do better than the subgradient minimization. Do you mean it was just faster, or do you mean it found a better answer?
It just seemed to be faster. And I can expand a little bit on that. So if you were to just kind of do just regular subgradient minimization, what you would find essentially is that, so this approach does sort of one step all at once, and then it finds the Q all at once, and then finds the theta, right? And the subgradient approach would kind of alternate between those two things. It would make a step of progress in the Q direction, a step of progress in the theta direction, and it would just alternate between those two. And it seems, at least on the examples that we tried, is that doing things all at once got you to the answer faster than doing a step of one first and then a step of the other.
But you're saying that R often has many local minima, and this only is applicable when R is convex. Right?
No, it has many minima, but not many local minima.
Oh, you're saying that they're contiguous or something?
Yeah. So all of the examples I gave you are convex.
Confused by, so like your previous slide, you're showing how, as you change alpha, you're going to get closer to the optimum, but only in a sense that is meaningful in terms of that regularizer.
Yeah.
Right. That theta, your regularizer theta is kind of arbitrary, right? It doesn't have anything to do with the real solution to the problem.
Right.
And by steepening it, does that really mean anything? I guess it means something in terms of the particular expression, but
Right. Yeah. So I would say a couple of things. One is that I would appeal to. There's a number of sort of online learning algorithms that play the same trick, which is that their convergence guarantee is in terms of how strongly convex the objective is. So we have the same issue, I guess. So that's one thing I would say. And And the other thing I would say is that if you if you have enough time, right? So there's two terms here. There's alpha and there's also epsilon, which is how accurate each step is. So if you have enough time to get an order alpha approximate solution, then this distortion that's imposed by increasing alpha is not going to hurt you. You know what I mean?
So I can think of semi-supervised like algorithms that give you non-convex R, like multiple instance learning.
Yeah.
Yeah, so this is, but you can still do epsilon subgradient, even in those cases, but I guess there's no theorem that says how accurate you'll end up, because you might be truly a local.
Right. Well, definitely, and I think that would, and that would still apply here. So I haven't even, so this theorem applies to the meta algorithm. How I'm solving each of these steps is not.
You haven't wrapped to the.
Yeah. Go ahead.
So is the alpha and the epsilon, are they coupled in some way? So if you make it steeper, the epsilon, you practically have, epsilon is an input in some sense to the theorem, but in practice if you were to change the steepness of the R, then the effective epsilon you had before you changed the alpha would be different.
Yes.
And so these two things are kind of coupled in a kind of an interesting way.
Definitely. So they're independent parameters, but this theorem is telling you that they had better be coupled. Like they had better be the same order if you want good performance.
And so I guess the question is when you can get them to be a useful bound out of the theorem.
Right. So
you wanted a certain epsilon.
Right. So this epsilon is governing how approximate each step of the algorithm is, and typically that's just a matter of time. So the longer you run it, I'll explain this in a moment, but each one is just an optimization. So the longer you run the optimization, the more accurate it's going to be. Okay, so there are these two steps, right? And I said if you solve each step pretty well, you get a good answer. But how do we solve each step? And it's not clear that we've won anything yet because I started with a mini-max problem and step one is a maxi-min problem. So how is that any better? Well, what's interesting is that for the loss functions that we're interested in, specifically log loss and hinge loss, we can turn this into something that's much more friendly. And what we do is we dualize, basically. We take the dual of the inner minimization. And so this minimization, I'm going to take its dual. And after I take its dual, for log loss, I get this maximization. And so this is the entropy of, let me just say. So this is basically very similar to maximizing log likelihood. So here, and the dual of that is maximizing entropy. And so here I'm maximizing entropy subject to these expectation constraints on the features. But now I'm not matching the empirical distribution, I'm matching this worst case distribution Q. And this objective has a nice form and sort of a well-studied form, and we can use existing algorithms like, for example, exponentiated gradient descent to solve this problem sort of just right out of the box. So that's step one. We dualize the inner minimization, and then we just kind of use a standard approach to solving the problem. And then once I found the worst case labeling Q star, I just plug it into here, and now this is just normal maximum likelihood. And I can use whatever I want, for example, stochastic gradient descent, to find the best parameter for this worst case labeling of the data. Okay, so now I'd just like to spend a little time talking about some experiments that illustrate the features of our approach. Okay, so we tried our algorithm on some image labeling tasks. These are both, and we compared our algorithm, on both binary and multi-class classification against some standard traditional semi-supervised learning approaches. And we did it using label noise that is both simulated and also some label noise that we got by submitting the data to labelers on Amazon Mechanical Turk. So for the first set of experiments, we tried it on a binary classification task. We compared our algorithm to some semi-supervised learning variants of support vector machines. The first is Laplacian SVM, and the second is transductive SVM. For our game algorithm, we used the regularizer that I talked about earlier. For each example, we gave a set of possible labels that it might have, plus a Laplacian regularizer. And in all the experiments that I'm going to report, the algorithm uses log loss for its objective, but in the results, I'll show you accuracy. Good.
The similarity for Laplacian was just some similarity function for the domain?
That's right, just on the features. So the first kind of label noise that we wanted to test against was an unhelpful labeler. And an unhelpful labeler is what we're trying to simulate is a person who erroneously, but perhaps sincerely, thinks that his best effort is in labeling those examples that are exceptions to the general rule. So this is the example that you wanted, right? So when labels are requested, they are labeled in the order of outliers first. More precisely, in decreasing order of the number of neighbors who are of a different class. So this form of noise labels outliers first. So it's a very confusing kind of noise. And we tried this on a couple of different image data sets. The first is the Columbia Object Image Library. This is a data set of household images. And the second is a data set of EEG brain scans. These are both data sets part of a standard semi-supervised learning benchmark. And to give you an idea of what an outlier in these data sets is, here is the most outlierish example in the Object Image Library data set. So these two classes are medicine cartons and toy cars. And on the right, circled in red, although it doesn't look like it, this is actually a picture of a toy car. It just looks like a medicine carton because of the strange angle of the image. So this is the first outlier in the data set.
So I'm confused. How do you encode order in an R? And all the algorithm sees is the R function, right?
Oh, right. So I'm going to label, say, 10. I'm going to reveal the label of 10 examples, and that'll be a trial. And then I'll reveal the labels of 15 examples, and that'll be a trial, and so on. And so I'll show you how the algorithms perform.
Run the algorithm just with different R's.
Different R's, right? And I'm going to show you how they perform as more and more information is revealed. And what I'm telling you now is how is that information revealed. So in the trial that reveals the least amount of information, I just show you the outliers. And in the trial that reveals somewhat more information, I show you, those plus a few more, and then plus a few more.
So if you reveal a subset, how is R of truth within epsilon of R of your best Q? So let's say in this example, you just label the rear view of the toy car.
Yeah.
Right?
Yeah.
So how is R defined? So for that being toy car,
yes,
and that's sort of half of all possible of R, that's the domain.
Yes.
Right. And that's 0.
Yes.
And then the other half is infinite.
Yeah.
Oh, and because you're not lying.
I'm not lying. No.
The truth is in that thing.
Yeah. I always reveal the correct label.
I see.
But they're just very misleading examples.
Yeah. Okay.
Right. So this is kind of what the data looks like. And so here, so here we are on the. This is actually the brain-computer interface data set. So, so on the x-axis, I have how much of the training set I've revealed or labeled. And again, this is in order of hardness, so the hardest first and then so on. And again, let me point out this is a very challenging kind of noise, so this is why the accuracy levels are fairly low. But generally speaking, the game algorithm does better than the other methods, although as the amount of the training set that is revealed increases, their performance tends to converge. Sorry.
It's the case that in this experiment, although that the labels that were revealed were misleading examples,
yeah,
but still the global statistics in terms of the fraction of, say, positive and negative example was reflective of the truth.
I didn't, not necessarily. I guess I didn't check explicitly, but we didn't enforce that in any way.
That's not my question. Do you know what the prior is on this? What is the fraction?
It's 50-50.
It is 50-50.
Yes.
Okay.
Like like in repeated trials, what changes? So like you have error bars, right? So
Yes. Oh, I mean, so for example, so we are subsampling a fraction of the data. Yeah. So that's where the noise comes from.
So you subsample and then rank based on outlierness.
That's right. And we have something similar on the image library data set. The gap is not as big here, but again, I would point out that at the very low levels of the training set being labeled, our algorithm does do somewhat better.
Uniform sampling.
Excuse me?
Uniform sampling. You compare your approach with Laplacian using uniform sampling.
Oh yeah. You mean the examples that are labeled are just chosen uniformly?
Yes.
Not in this experiment, but in a later one I do that.
Because here the results you report are much worse than what they were putting.
Yeah, for sure.
Because for this data set, I remember the accuracy for Laplacian is at least above 90% accuracy.
Yeah. No, that's definitely true.
Twisted. This is.
Yeah. It's like finding the most
No, for
outlier.
the sample learning benchmarks, you just do uniform sampling.
Yeah, that's right.
Yeah.
That's not this.
Yeah,
This is almost but not quite lined.
Yes.
If you only choose the worst part, that means if the label point only close to the boundary, I think SVM can do much better job here, right?
It's not necessarily the boundary, right?
Yeah,
Because
Yeah, I
the
thought
boundary was
weird.
if it was linear separable.
Right.
Here it's going to be on the other side of the boundary.
Yeah.
It's errors. He's labeling almost like errors.
Great.
But I do show some results for uniform sampling on a different data set, so maybe that might address.
In this presentation, you mean?
In this presentation, yeah, just a little bit. So in the second set of experiments, we tried it on a multi-class data set, and here we compare to some semi-supervised algorithms that try to infer the missing labels using a kind of maximum likelihood approach. And so here the kind of noise we wanted to test against was a labeler who is reluctant to label examples that seem to be ambiguous. So here, the labeler is going to label examples on the border between two classes last. So as the number of examples whose labels are requested increases, the labeler labels examples in increasing order of the distance from the centroid of the class cluster. That's the precise definition that we're using here. But generally speaking, this labeler is avoiding the border regions, which are the harder examples. So this is a guy who's reluctant to label hard examples. And we tried this on a data set called Faces in the Wild. This is a data set of facial photographs of public figures. The features are the eigenfaces. And so just to give an example of what a border region between two classes look like, these are the two classes in our data set that had the largest border region by our definition. And they're Arnold Schwarzenegger and Gerhard. This is the former German Prime Minister, Gerhard Schroeder. And they kind of look alike, right? I think they do. Okay. So here are the results. And so again, this is a 10-class example. And again, we're reporting accuracy. And I would say over the range of the fraction of the data set that's labeled, we're showing small but consistent improvement over the existing algorithms.
That one seems more surprising to me. It'd be interesting to see the Laplacian results on that one too, because there, you're kind of like, you're essentially giving it the good sort of labels, things that are squarely in the midst of the classes, right? And techniques like Laplacian, as you would hope, would kind of grow out in the right sort of way.
Right.
What's your intuition behind why game does better in this case? So it's not really such an adversarial solution here.
Right. Yeah, I think so. I think what game is basically doing is hedging, right? If you think of like EM, right? So what the EM approach basically does is it's trying to infer the missing label. And EM can get caught in a local minimum. And what EM does is it doesn't hedge at all. It guesses sort of wildly. I'm anthropomorphizing, but by getting caught in a local minimum, it's sort of being very optimistic. It's guessing some labels for the examples that are missing, and then finding that in fact I can fit those quite well. Whereas our algorithm hedges if there's uncertainty about.
The EM algorithm gets overconfident about its inferred labels, and then it treats the problem as though they're inferred.
Exactly. And the way that I label the data is that the examples that are missing are exactly the ones that you should be hedging on.
In the semi-supervised benchmark, there are 10 different data sets. So did you also try experiments on other data sets?
Yeah, well,
So a bunch of them are like synthetic, right? So like, I don't know, at least 3 or 4 of them are synthetic. And then we showed you 2.
2 are synthetic data sets, and the other 8 data sets are real data sets.
2? Okay.
Yes.
Yeah.
Data sets, the 2 Gaussian that have overlaps. Other data sets like some data sets like test data set, right?
Okay.
Well, that's extremely high dimensional data set. It's
Yeah.
very hard for semi-supervised algorithms.
Which ones are?
Text data set, text classification.
Okay, right.
So that's very hard for semi-supervised algorithms.
Is that the one that has a lot of classes?
Hard
Does it have a lot of classes, that data set? One of them?
classes.
2 classes.
Yes.
But a lot of features? Well,
the dimension is more than 10,000.
Yeah, right. Okay. So we selected 2 data sets out of those 8 real ones. We had some were practical considerations, like some seemed like too many features. I don't remember there being. I don't know. I can't say that. I don't remember the exact reasons why we selected the ones that we did. Okay, and finally we wanted to try it on some sort of label noise that comes from real people and not from simulation. So we selected from our faces in the wild data set, we selected a set of photographs for 2 celebrities who have a lot of photos in the data set, Laura Bush and Jennifer Aniston. And rather than showing these pictures to the labelers one by one, as is typically done in a labeling scenario, we wanted to simulate something more realistic, something more like the motivating examples I gave you in the beginning of the talk. I'm sorry, did you have a question? Okay. Something more like the motivating examples I gave in the talk. So we actually showed them all the pictures simultaneously in a sort of tile format, which is here, like this. And we said, label any 5 images you like, exactly 5 images. And so here what we're trying to test is, we want the users to select pictures in the context of seeing other pictures, and we want them to use their own biases and methods for selecting pictures to label whatever they like.
Did you tell them what the purpose of it was? Like, I mean, I'm just curious because you had made this earlier. You had said this thing about like, well, here's a user who's thinks they're being helpful by like getting these really hard ones or something.
Yeah,
so I'm wondering if you tried to motivate them by saying, hey, you're helping a learning algorithm, so do the right thing.
Right. No. So this is the entire task.
I see. So you just said label.
Yes.
Go
So
for it.
all the guidelines are right there.
I'm really curious to see, did you do an analysis of how many people just picked the first 5?
Oh yeah, I'm going to show you that.
Okay.
Well, not quite that, but something like that.
Okay.
No, so this is the entire task. And I think that you have to get a title, and I just said, image labeling easy. That was the title. Like easy meaning easy money. That's what I was trying to attract people to label. So this is what it looks like. And so the first thing to note is that there is indeed strong bias in how people choose pictures to label. So here I've ordered the pictures from most labeled to least, and the most labeled picture I think is about 3 times more likely to be labeled than if they were being labeled at random.
What was the presentation order?
This is not presentation.
No.
Was it fixed or
The presentation order is fixed. It's this.
It's a fixed order.
But is that picture number the presentation order?
No, it's not.
You've just sorted it.
I just sorted it. Yeah.
Oh, I
show
see.
you
Do you
the-
know what the relation is with the?
Yeah, I'll show you. in a
Oh,
second.
okay.
Yeah.
How was that picture chosen?
This was just arbitrary. I can't say I've chosen it specifically. Just a mix. So this is to demonstrate that there are biases, and let me kind of pull out 2 kinds of biases. So the first is that Jennifer Aniston's there were an equal number of each kind of picture, but Jennifer Aniston was much more likely to be labeled. And the second kind of bias is, I think, what you're getting at, which is location on the web page. So
It's not that strong. So I would have expected it to be even stronger than that.
okay, well, it might be influenced by the fact that the submit button is at the bottom of the page.
Interesting.
So we think what people did is they click on a bunch of pictures on the top.
And what would happen if there's someone labeled more than 5?
Oh, so if someone, that didn't usually happen, but if someone labeled more than 5 or they made a mistake, I just discarded the trial.
Oh, okay.
So I'm not interested in that.
How are top, middle, and page then? It's getting interesting. I mean, essentially 50-50, right? It's 50% is top of page, 50% not top of page, so maybe it's not. I mean, I would have expected an even stronger effect.
Yeah, I think like you're saying, basically we think people clicked on some things, scroll to the bottom, clicked on some things, and submit. Go ahead.
Or did people mostly label one person, or would they do both? Like, would they do just pick out all the pictures of one person, or?
That's a good question, actually.
I don't know. I didn't think of that. That's a good question.
I mean, it doesn't matter, but I'm just curious.
So here's the performance if you run the SVM variance and our algorithm on this data set. These are box plots over all the trials. So not only is our algorithm doing somewhat better on accuracy.
So each trial is one labeler here?
One labeler,
okay.
Yeah. These are box plots. So this is giving you, the whisker plots are the range. The whiskers are the range, and the top and bottom of the boxes are the 75th and 25th percentile of the accuracy. So we're getting somewhat better accuracy and also more tight range. And maybe to address what you were saying earlier, what if this data was just labeled uniformly at random, right, rather than in this biased fashion? So we tried just labeling the data uniformly, and then the advantage of our algorithm basically goes away.
How to choose the parameter for Laplacian?
Excuse me?
How to choose the Laplacian parameter? Right?
Yeah, so we did some cross-validation.
I guess you have enough data to do that.
Yeah.
So the Laplacian here is normalized Laplacian or unnormalized?
Is it normalized or unnormalized? I think it was normalized. When you say normalized, you mean, so we take the distance, and then we exponentiate the distance, and then we have this scaling parameter that controls the dynamic range. That's the kind of Laplacian
No,
we
you
use.
have to divide by the square root of the
Square root,
integrate
yeah,
of each node.
Oh.
That's the normalized function.
Oh, I see. I don't remember. Sorry.
Do you think that the reduced variance that you see with the game outcome, do you think that's meaningful, or would you expect that, or is that just?
So I think it's intuitively meaningful, but I have no theoretical results to explain why. So the reason it's intuitively meaningful is that for example, unlike the transductive SVM, it's a convex problem, and so it's minimizing a globally convex objective. Transductive SVM can get caught in local minima. So that's a partial explanation.
So for the transductive, you use the software by Contextual?
Yeah, that's what we use.
Actually, Olivier pairs transductive can work much better.
Excuse me?
Olivier pairs transductive SVM.
Oh,
Can work much
who is that?
Olivier pair.
Olivier
Actually,
Chappelle.
he proposed the benchmark. He proposed the semi-supervised learning benchmark. And he also implemented transductive SVM in a different way.
Oh, okay, I didn't know that. No, I just used Thorsten's okay, so that concludes the semi-supervised portion of the talk. If I have time, I don't know if I do, I can briefly talk about some of the work I've done on bandits.
There's some slop time.
There's some slop.
People may have to flee.
Okay. All right. So should I just go ahead? It's just a few slides. Okay. So in my PhD and also my postdoc, I've worked on some bandit algorithms for sponsored web search. I'll describe a couple of the projects that I've worked on, just very briefly. So the formulation of the problem is as a contextual bandit problem. So what is a contextual bandit problem? Well, it's a problem, a decision-making problem that proceeds over several rounds. And each round, one is supposed to choose one of several actions. And depending on the action that you choose and also an exogenous context, you receive some payoff. So you can imagine walking into a casino, you're faced with all these slot machines. You choose one slot machine to play each round. And then, this is where the analogy falls apart. There's some context that also affects, both the context and the choice of slot machine that you made affect your payoff. So where, the context is fully observed. Yeah. And this learning problem was formulated and was motivated by sponsored web search because it's an excellent model for sponsored web search. So sponsored web search, in this model here, the actions are the advertisements that you can choose to display to a user coming to a search engine. The context is the query that the user input to the search engine, as well as anything else on the search results page. And the payoff, the expected payoff, is the click-through rate, the probability that a user is going to click on the ad, given that that's the query they searched for and everything else. Okay. So we've addressed two kind of challenges of these contextual bandit problems. The first is that in any realistic setting, the number of actions and the number of contexts is going to be very, very large, because that's the number of ads and the number of queries, and of course that's enormous. And the second challenge that we address is that click-through rates are usually not stationary, but rather they can change over time. So I'll discuss a solution for each of these problems briefly. So the click-through rate of any ad is a function of both the features of the ad and the features of the query. And so here we have, a search, tickets to Seattle, and here's an ad, flights to New York. So we want to estimate what is the click-through rate when this ad is presented in response to this query. And the basic problem is that we can't just use counts because the number of distinct ads and queries is enormous. So we have to do something to generalize. And so our approach, and this I just have one slide on explaining our approach, is that it's that the functional relationship between the click-through rate and how that depends on the ad and the query decomposes in some nice way over the words that are in the ad and that are in the query. And so this graph, so we have this graph, and we place an edge, and so we have a node in this graph for the words in the query and also for the words in the ad. And we place an edge between two words if we think the click-through rate depends jointly on those two things. So for example, the click-through rate is going to depend both on the fact that there was the word tickets in the query and the word flights in the ad. And I'm sorry, go ahead.
So are you saying this edge is an input? You are determining where the edges are, or the algorithm?
Me and the designers. Yeah, this is an input to the algorithm.
Okay.
Oh, I see.
Yeah. So yes, this is all prior information about the problem that is being coded by us, the algorithm designer.
Well, you don't know the way you just say the edge exists.
Yes, that's right. You don't know the way you just have the edge exists. And likewise, the fact that Seattle is in the query and New York City is in the ad has some effect on the click-through rate, probably has a downward effect. And the fact that the word cheap is in the ad, this graph is indicating that has some effect on the ad that's independent of what was in the query. Go ahead.
And decomposition, if you have multiple edges connecting them in cycles and so on, do you assume that the decomposition is always just in terms of edges, linear in edges, or if you have more complicated structure, if you have...
So here's what I'm really assuming, which is that I assume that the function decomposes into a bunch of terms. Each term depends on only a few words. And then if two words appear in a term, I put an edge between them.
So you can have a full factor graph where each term would be a factor and it can be connected to any number of words from either.
That's right. That's right.
So here, just to make sure that I understand, so here it might as well be the full two-sided graph, right? So right? You mean you would like to assume that you don't need to look at long term, like cheap flights.
Yes.
But cheap could be connected to any green term, and so there could be all the links going from the greens to the reds could be in the graph.
That's right. That's right. Any edge could be in the graph, and then the regret and the complexity of the algorithm will depend on how sparse the graph is.
So kind of the assumption is mostly around the fact that it is two-sided.
No. So I made it two-sided to make it look good, but you could have edges between two things on the same side. But so you're going to have a graph. It could look like anything you like, and then the regret and complexity of the algorithm will depend on terms that perhaps you guys are familiar with, things like the tree width of the graph and the degree of the nodes in the graph. Or
can the singletons still be involved as elements of the overall function as well, or are they?
No, they can be involved.
Oh, they can.
Yeah. And so this is exactly the kind of assumption that one makes in graphical models by encoding independence assumptions about a distribution. But here we're...
Perhaps a more a representation that would better fit for describing would be like the factor graph.
That's right. That's right. But you could, so you can take your factor graph and then you can make it a graph by just adding edges between everything in the same factor. And we like that representation better because our bounds are in terms of properties of that graph, not the factor graph. And so here I'm just repeating what I just said a moment ago. We have an algorithm that exploits the structure of the payoff function. And this algorithm this is a contextual bandit problem, an algorithm for selecting an action to take in every round. And both the running time and the regret of this algorithm are going to be polynomial as long as this graph structure is sparse. And more precisely, it has low tree width and low degree. Go ahead.
Sorry to keep asking about this factor graph thing. I want to understand if I understood what they were saying correctly. Can you go back one?
Yeah, you
Can you have a factor, like if I think that's important to have cheap flights and New York City all at the same time or not at all, I can express that in your formulation.
You can.
And how would you split that out into?
So that would be a clique.
That would be a clique, right? So you're allowed to, you're allowed to have functions over these. Okay.
Yeah, that's just a measure of sparse potentials. It's just lower potentials.
Yeah.
Okay, that's right.
Okay, and so that's all I was going to say about that. This is obviously kind of a quick tour.
Was there some interesting result? You proved polynomial on tree width. Was there an empirical result or something?
No, it was just a theoretical result. But to the best of our knowledge, this is the sort of first end-to-end algorithm for contextual bandit problems where the number of contexts and the number of actions can be very large. And by end-to-end, I mean that we don't make any assumptions about access to an oracle that can solve some problem that maybe we can't solve. This is sort of a full solution and exploits the structure of the graph. Okay.
Right, you can have arbitrary properties of either and just define the combinations in any way you want.
Sure, yeah, you bet. So the second kind of problem that we wanted to deal with in contextual bandits is that these click-through rates typically are not fixed over time. They change, right? The rate at which people click on things changes over time. And in the study of bandit algorithms, when you're talking about the payoffs changing over time, there's usually two kind of extreme forms of assumptions that people make. One is stationarity, that these payoffs or these click-through rates are fixed for the entire duration of the interaction. And the second is the other extreme, which is that these click-through rates can change every single round, and they're changed even adversarially, right? And so for us, these assumptions are either too weak or too strong. And in our view, it seemed like a more realistic assumption is something that's kind of in the middle, which is that for many queries, click-through rates they can change abruptly, but only rarely. So let me give you kind of an example. So before October 2009, the query Balloon Boy, if you were input it to any search engine, would give you a company called Balloon Boys, which is they make rooftop inflatable advertisements. You've probably seen these things. But in October 2009, if you guys were watching the news around that time, there was this kid in Colorado, I think, who went up into the sky on this sort of handmade balloon. Or no, he didn't, right. They thought he did, but go ahead.
This captures half of the change, right? But it seems like there's a huge other factor, which is, I don't know, seasonal effects and these kind of things where a ton of queries change slowly, but they're all changing every day.
Yeah, you're right. So this work is focused on the kinds of queries that change abruptly and suddenly, not the ones that follow a kind of rhythm. You're right. This is not well suited to that.
You can apply what you did to that, or is it's really targeted towards the abrupt?
We did, and we found it doesn't work so well for the cyclical.
Okay.
It's really designed for these abrupt. Right. So what's interesting is that the meaning of this query changed very abruptly, and therefore the associated click-through rates changed very abruptly. But this change was not like the change was associated with all kinds of other signals that were indicating that the change happened. For example, the volume of the query spiked, the occurrence of this query in news articles spiked, and so there was lots of indications that something has happened to the query. And so our approach, and this is work I did while I was at Search Labs in Silicon Valley for one summer, which is that we combined an online prediction algorithm with a bandit algorithm. And so the prediction algorithm uses these contextual signals like the volume of the query, its occurrence in news articles, and so forth, to predict whether or not the meaning of the query has recently changed, and therefore whether its associated click-through rates might have dramatically changed. And then that prediction algorithm outputs a prediction, and then our bandit algorithm takes that prediction as input and decides whether or not it should modify its behavior accordingly.
In here, optimal is the optimal constant backward looking over the usual thing you compute with regret.
Yeah, this is the algorithm that knows the option that has highest click-through rate, and it just offers that.
Yeah, but
the best payoff.
It's even sort of super optimal. It's not even assuming that it's a constant click.
Oh yeah. This is right. This is not the best single ad in hindsight or anything. This is every round.
So this is the optimal node of future.
Yeah. Well, it knows. So there's all these options, and they each have some click-through rate. It knows which is the best one.
No, but on what period do you compute the click-through rate, right? If you...
Oh, I see.
Is it every
so in the experiment, the granularity is a day. So.
Oh, okay.
So we know that today's click-through rate is going to be this. Yeah.
Wait, why would the best one in hindsight be any different than the optimal?
Because the best one is changing in this experiment.
No. But if you're only giving an answer for that day's, are you?
Yeah. We're only giving an answer for that day. But I think John was asking, are we?
Because usually the way you do regret is it's usually the best constant algorithm. So you would average the whole click-through over the whole data set. Yeah. But that's not where you're doing something even harder. Okay.
Yeah, okay. And we find that using this online classifier to predict when changes are happening, and then modifying the bandit algorithm to use this information and take advantage of it, can result in some dramatic improvements in the regret. And that's all I had. Thank you very much.
Have